Okay, so I prepared in advance a picture, right, of this related to this problem. And so what do we have? Again, it's about cyclotron motion. You remember when charged particle moves perpendicular to the magnetic field, right? So what do we have here? An electron. That's our charged particle. Then there is a uniform magnetic field. You see magnetic field lines are up, B. And the value of the magnetic field is given 30 millitesla. Right. Then I oriented my coordinate system. You remember you have constitutional freedom to choose any coordinate system you want and orient it in any way you want to make your life a little bit easier. So I oriented in such a way so that my z-axis is along the magnetic field lines. And as a result, this is y, this is x, and again, this is the right-handed coordinate system. Right. Then our electron flies into this magnetic field lines, or through the magnetic field lines in this direction. This is direction of V, and it makes an angle theta. Okay, the problem says with xy plane, but I slightly adjusted, and so it's just above the y-axis. It doesn't change generality. We're not losing any generality. So I drew it like this. So this angle is 30 degrees. And the speed is given. So now, right now, I cannot write what needs to be found. And that's why I didn't write. So let's first analyze what are we going to observe, right? Draw it. And then only I will be able to write what needs to be found, right? So which trajectory are we going to see here? It's related to the previous class material, right? You remember when we discussed northern lights, right? So you remember our particles was entering magnetic field at some angle which was neither perpendicular. Okay, and particles were entering magnetic field lines neither perpendicular nor parallel, right? And that's what we have here, right? So you see, velocity is at angle 30 degrees. So in order to analyze this situation, what did we do when we discussed northern lights? We decomposed this velocity into two components: perpendicular to the magnetic field lines and parallel. Right? Okay, let's do it. So let's say this is my perpendicular, and let me call it V sub y. Okay, because it's along y direction, right? That's how I label it, yeah. And this will be component V sub z. Okay, let me show them as vector. So I can, of course, decompose V as V sub y plus V sub z, right? And now, which trajectories are these components going to give us? V sub z, when particle moves along magnetic field lines, of course, it gives us just a uniform translational motion. It's like I told you, right? So remember, if you send a charged particle through the axis of through the solenoid parallel to the axis, of course, it is not going to experience any magnetic force, right? It will just fly straight along the same direction with the same speed. So V sub z is going to give us a uniform translational motion. But V sub y, since it is perpendicular to the magnetic field lines, it is going to give us a cyclotron motion, circular motion. So now if you superimpose these two motions like we did yesterday, right? So we're going to get helical motion. Circles with displacement, circles with displacement, circle with displacement. So helical motion. So let me draw that. And I guess I will use still blue. All right. Yeah. All right. So let me draw it nicely. So it will be something like this. Right. So that's our helical motion. Right. And also, let me write down sort of in words what does this velocity give us, and what does that, and what that velocity gives us. All right. So which way I wrote it? Okay. I will write like this. So V sub z, of course we can easily find it because this angle is given, and that is basically a side which is opposite to the given angle. And this is just a right triangle, right? So V sub z, of course, we can find it as like V times sine of angle theta. And which way I wrote it? I will write it. It's a component parallel to B, right? And it gives us a uniform translational motion. Uniform translational motion. It's that boring motion which, yeah, we know how to describe. It's nothing fancy. Right. And now V sub y. Let's write similar for V sub y. Of course, we can easily find it. It will be V times cosine of angle, because in order to find adjacent side, you need to use cosine function. V times cosine theta. And again, I want to emphasize it's a component perpendicular to the magnetic field. And of course, component perpendicular is going to give us cyclotron motion, which is uniform circular motion, right? Cyclotron motion. So let me write. So it's a cyclotron motion, uniform circular motion. So that's, and of course, if you superimpose these two motions, you're going to get this helical motion. And now, finally, after discussing this, we're ready to write what needs to be found. So what we need to find, cyclotron radius R S Y C Y C. We need to find cyclotron radius. And it's not enough to describe this helical motion completely. In order to describe this helical motion, we also need to know what is called the pitch, which is this distance. You see this point, for example, and this point, right? And the distance between them is called the pitch, P. So, P. Okay, it's a PITCH. So that's what we need to find. If you know a radius and if you know pitch, pretty much you know everything about this helical motion, right? So let me check if I gave everything. Yeah. So now, cyclotron radius. Actually, we derived the formula, but I don't like using that formula because it's not something fundamental. Every time in physics, you need to know only remember fundamental equations, and then you can juggle those fundamental equations, and you should be able to describe easily. Okay, maybe sometimes not easily, but in this case, easily. You can get the formula for the cyclotron radius. Right. So let me just quickly derive it because it's a 1.5 lines. So Newton's second law for the radial direction. So remember, okay, so it's F equals m times acceleration in the radial direction. So this is force in the radial direction, right? So which is force? Okay, let me write F R. It's our magnetic force QV cross B, right? Okay. You know what, I don't want to use the bracket. And I will stop for a second over here and ask you this. Are you okay with what I wrote? And also I can write centripetal acceleration, right? A sub r, you remember? Formula V squared over R cyclotron. So what is missing in both of these formulas? What is, we have to adjust it because right now it's not completely wrong, but not completely true at the same time. Look, guys, In these formulas, when we analyze that and when we describe cyclotron motion, every time our velocity was perpendicular to the perpendicular to the magnetic field lines. Now velocity is v. This v is neither parallel nor perpendicular, and we decompose to v sub z and v sub y. And this cyclotron motion, which we're trying now to sort of describe, is described by the v sub y. We need to use this component, right? So over here, there must be subscript y. Over here, there must be subscript y. Right? In this problem, you have to be careful, and you need to realize which component of the velocity you have to use in this or that part. Right now, we're describing the circular motion, right, cyclotron motion, in order to find cyclotron radius. So now, if you just leave v, it's wrong. Right? You need to use v sub y. Okay, so you know what? I even use different colors. So v sub y to emphasize. So v sub y. Okay, it's one part where students make mistakes, right? Okay, and of course, since v sub y and b are perpendicular, right? Right, so I can write, so v sub y is perpendicular to b. Of course, we can write force as q v sub y times b, right? Because sine of 90 degrees is 1. Right? Okay, so now we can plug it, of course, here. So it will be q v sub y b equals to mv y squared over r cyclotron, right? So of course, from here we can get the cyclotron radius, right? So that's basically how I derive it in the class. So r goes up here, so it will be mv divided by qb, mv sub y divided by q times b. Right. So of course, you see pretty much it's this, and then you can write immediately that, and it's 15-20 seconds of work. Right. And again, v sub y. So you can plug, of course, numbers. I'm not going to do it. Right. Mass of an electron, of course, you know, magnetic field is given. Velocity, of course, you can calculate. It's a v sub to v times cosine theta. Right. V times cosine theta. If you plug all that, you will end up with 0.82 millimeters. It's quite a small radius, right? Less than a millimeter. So the particle spirals with that radius. Right. Okay, so now we answered this question. What about the pitch? So now that's where most of the troubles are. And if I don't discuss this problem in the class, I start getting emails from students, of course, unless they use check, right? But in that case, right, it's easier. How can we find this distance? So basically, we have a superposition of two motions, right? Yeah, this uniform translational motion and this uniform circular motion, right? So it gives us helical motion. Which parameter or which quantity connects both of these motions? And actually, that parameter connects everything on the face of the Earth. Which parameter I'm talking about? It's time. Time connects them all, right? And look, let's try to follow the particle. So let's say the particle is over here, right? So, and it starts completing next cycle of motion. So it moves basically along the circle, and also at the same time it displaces itself in this direction by the distance, which is pitch, right? So at the same time it completes the circle, and also it displaces itself by this distance pitch. So what can you tell about this travel time between this point and that point? It is equal to the period of the cyclotron motion. So it's the same time as it takes for a particle to complete a circle in the cyclotron motion. But at the same time, this particle moves in this direction, z direction, over this distance p, right? So pretty much the travel time between this point and that point equals to the period of the cyclotron motion. So that's why I studied that time connects both of these motions, right? So it takes, I don't know, period to complete a circle, and also at the same time it displaces, a particle gets displaced by the distance pitch. So in order to find the pitch, we need to find first the period of the cyclotron motion. And we also know how to do it. We discussed it yesterday, right? Okay, so that's the second part where, yeah, lots of troubles, right? So realizing that period of the cyclotron motion, it's also a travel time between this point and that point, right? The first part that you need to keep track of which subscript you use with the velocities, and this is the second part. Okay, so now that was our cyclotron radius. So now we need to find the pitch. But of course, first we need to find the period. All right, so period, so t equals, right? And again, you remember how can we find period? Because even after discussion, if I give a problem like this on the exam, okay, in the past, I remember still some students panic at this point because they think, okay, period is something complicated, right? So, but in this case, you remember it's very simple because we have cyclotron motion. It's a uniform circular motion. Particle moves with the constant speed along the circle. So in order to find the travel time over the circle, you just need to take the total distance, which is circumference, and divide it by the speed, because the speed is constant. The particle moves with the constant speed, right? So we discussed it yesterday, you remember, right? So the period is circumference, which is 2 pi r cyclotron, divided by the speed. Which speed? Again, every time when we get to the point of velocity, I keep bugging you because, yeah, it's very important. We are discussing the cyclotron motion, right? So it's a y component. V sub y is responsible for this circular motion. So over here, of course, we must use V sub y. Not just V, because I see plenty of times students just grab the first V which is available in the problem and shoved it into the formula. No, it's so V sub y, right? Okay, so it's a 2 pi r cyclotron we just found, and so it's a V times cosine of angle theta. Right. Again, you can plug numbers, and I will look at my notes. The answer will be 1.19, okay, with 3 sig figs, times 10 to the power of minus 9 seconds. So it's a almost 1 nanosecond. So a particle circles. Okay, it takes almost 1 nanosecond to complete one circle, right, in the cyclotron motion. And it also takes 1 nanosecond for a particle to move from this point to that point in this helical motion. So now, and again, so how can we find the pitch? Because the key word now, we have uniform translational motion. Uniform translational motion, it means that the particle moves with the constant speed in this direction. V sub z is constant, right? So P equals V sub z times dt period. So now pitch equals V times t. And again, on purpose, I mentioned V sub z, but now again, I want to emphasize. So guys, here now, there must be z, because that's the speed with which particle is displaced in the z direction, right? So V sub z. Because again, in the past, I saw students just grab V. Okay, so in the formula Z, no, actually, if students don't come to the classes, they usually don't come to this point, right? Right. But I saw, as I told you, then they just use the velocity which is given, right? Plug it here and call it the cyclotron radius. Okay, so this is, of course, I can write it's a v times sine theta times the period, right? Of course, you can plug numbers, and I will look at my notes. So it will be 3 times 10 to the power of negative 3 meters. So that is 3 millimeters. Right. So it has cyclotron radius less than a millimeter, and in this direction over each cycle, it gets displaced by 3 millimeters. Okay, usually I assign this problem also as a homework problem, so that students can just practice by themselves at home. Okay, so if you have questions, need additional explanations, okay, tell me. Now I just want to quickly discuss a couple of conceptual questions very quickly, and then we'll move back to the slides. I just basically wanted to discuss this. So these are conceptual question 6. Now, CQ6. So what if we have this uniform magnetic field? So B, right? And let's say we have a particle, positive. Okay, for example, proton. All right, let's say we have a proton, positively charged particle, enters this field this way. All right, so this is the velocity. Okay, charge Q. So we need to answer, okay, so the sketch a trajectory. In which direction trajectory is going to be bent, right? Again, it's just a application of the magnetic force, Q, V cross B. B direction is given into the board, V that way. So right-hand rule, V, and this is the correct orientation to bend my fingers in the direction of B. And as a result, magnetic force is going to be this way, bending our trajectory in this direction. So this will be the trajectory approximately, right? Or if, for example, the situation like this, trajectory is given, and we don't have information about the charge. We don't know if this is an electron or proton, for example. So how can we extract that information? It's like we discussed in in the first half of the class. In order to find information about the charge, you just need to look carefully. Direction of the V cross B. V cross B, it's up, right? And then if you see the trajectory, of course, by looking at the trajectory, of course, you can tell immediately that the force acts that way, right? And in this case, force and direction of V cross B, since direction of the force and direction of V cross B are the same, so it means that it can be possible only when the charge is positive, right? That's how we can analyze it. And then the next one, quickly, so this is part A. Now part B, and then I will switch to the slides. So now let's say magnetic field is presented by these dots. Right. And let's say particle now negatively charged, right, charge Q, enters into this magnetic field with this velocity v. So again, we need to answer the question, can we sketch a trajectory? The same, we just need to find direction of the magnetic force, and that, since that is the only force acting on this particle, neglect the gravitational force, right? So that force is going to determine the trajectory. So V cross B, again, V is up. This is the wrong orientation, so I need to position my hand like this so that I can bend my fingers towards U. So now I have to position my hand like this. So V cross B, and my outstretched thumb gives me the force, direction of the V cross B, right? So this will be, let me use green. So that is V cross B, right? But you remember, when you analyze direction of the force, is not enough just to look at V cross B. Then, you remember about my 1.5 steps. Then, after that, you need to look quickly at the sign of the charge. In our case, charge is negative. So it means that in order to find direction of the force, we need to flip this direction V cross B. So the force will be this way. So the force is this, right? And as a result, trajectory, of course, is something like this. So that will be trajectory. Or, of course, as I said, it's possible to have sort of reverse situation. The question can be extract information about the sign of the charge. Is it positive or negative, right? So in this case, what velocity, of course, trajectory is given, right? Of course, you can get information about the velocity because all the time it's tangent to the trajectory. Information about the force you can get again from the trajectory because it is bent this way, so it means that force is this way, right? And so now, and of course, magnetic field information is given about the magnetic field. So again, you need to compare direction of V cross B with the direction of the F, with F. So F that way, V cross B will be that way. So you see, they are in opposite directions, and it's possible only when charge is negative. So in this case, you can get also information about the charge. The problem is stated differently. Okay, so enough. After this, you should be comfortable analyzing these trajectories and extracting information about the particle.